not live.
I'm not live. Okay, great. So I'm going to put the word torus in parentheses because, the technique that I'll introduce today, I'll work more generally, but how generally, I don't know. Okay, so the invariance I want to talk about today, this link homology I want to talk about is the the HOMFLY version of Khovanov-Rozansky homology. So that'll be an oriented link to define to actually construct the link homology, you need to choose a braid representative. So let's write L is the closure of a braid. Some number of strands N. So Khovanov-Rozansky in 2005, they construct a triply graded homology theory for links. So they define an invariant that I'm going to call triple H. Which a priori depends on the braid representative, and show that it only depends on the link up to isomorphism of triply graded vector spaces and overall gradient shift. The gradient shift you can fix by normalization, it's no big deal. So from the triply graded, so this invariant categorifies the HOMFLY polynomial in the following sense. So associated to a braid, we have the Poincare polynomial, which is, in this case, it's a series. So as it turns out, so for knots, there is a reduced version, which is finite dimensional. For links, though, you can't avoid infinite dimensional vector spaces. So the Poincare polynomial, in this case, really is a series. So it'll be supported in finitely many homological degrees. It'll be supported in finitely many degrees for two of the gradients, but then the third gradient, the Q gradient, will be sort of unbounded. Okay, so you define the Poincare series like so. Sorry, that's a dimension of HHH, the degree IJK part of the HHH space. Then this satisfies the following property. So if you plug in t equals -1, what you're really doing is you're taking the Euler characteristic of their homology, and this is the HOMFLY polynomial. HOMFLY BT polynomial. The braid closure up to normalization. Is there a question?
You say what the scheme relation looks like in these variables?
It's not going to really be relevant. Sure, I can. Yeah. So I hadn't planned on talking about it. So it depends on your sort of preferences.
It is okay. Can you say what the answer for the trefoil is?
Yeah, I'll compute the trefoil multiple times.
That'll be enough.
And let me just say that the unknot as invariant. So for now, I can say that's quite easy. So it'll be an infinite series, and the Poincare series will be rational. Okay. So, what's the best way to do this? Do I move that under? Let's see this. words have momentum. Or inertia. Okay. Should be careful to use the right word. I'm a luminist after all. Okay. So what's the goal for today? The goal for today is actually fairly modest. So let me just observe the following. So this guy, and I will sort of give you a rough sketch of the definition later, but it's actually nearly impossible to compute from the definitions. Okay. So very hard to compute. But some progress was made sort of in the recent couple of years in performing computations. So I want to kind of outline some of these results here. So first off, in 2016, me and Ben Elias sort of introduced a new technique for computing these things. This was like in March or April of last year. And then in April of this year, so I should say we used this technique, we kind of illustrated it to compute the homology of the end-to-end torus link. So it's actually, if you've ever tried to compute things with Khovanov-Rozansky homology or even just Khovanov homology without a computer program, computing them in any infinite families is actually really hard. So you can do like 2n torus knots, or for fixed braid width, you can usually compute them in some infinite families that way. But this was like the first family of examples where the braid width goes to infinity. So we're pretty happy about that. And then, in this paper a couple months ago, maybe last month, I took care of the case T and M. So torus links, I should say positive torus links. Took care of this case where M is nk or nk plus or minus 1. Okay. And then very recently, like a month after that, Anton Mellit blew me out of the water. No, so he can compute it for all. Well, in his paper, he asserts that he can do it for torus links, general links, but he actually only proves it for torus knots. Again, positive. Now, and then all of these computations use the original technique. Yeah. So my goal for today is to translate Mellit's idea, because this paper has really, cool ideas, but it's a little bit hard to read if you're a topologist, or the ideas are combinatorial. But anyway, I wanted to translate it and then show you how it does actually extend pretty easily to links. So that's the goal. So I'll state the technique, and I'll tell you Mellit's idea. And then you'll know how to compute all torus link homologies. Okay, but before I do that, let me say why you might care about this stuff. So why? Well, first off, the technique is not actually limited to torus knots. It works in some level of generality that we don't really know yet. So this could eventually be like a powerful technique for computation in general. And maybe you don't care so much about triplet graded link homology, maybe you care more about like knot-floor homology or something like this. Well, conjecturally there's supposed to be a spectral sequence from a reduced version of triplet graded homology to like not full homology. Hat probably. So this is conjecturally spectral sequences. And there certainly are spectral sequences to the SLN versions of Khovanov-Rozansky homology, constructed by Jake Rasmussen. So as it turns out, even though the definition of the triple graded homology is actually a lot more complicated than any of those, computations are seeming to come out kind of easier in this setting. So if you do computations in the triple graded homology, maybe by doing some spectral sequence argument, you obtain some computation of some other invariant you care about. Okay, but of course we need to construct that first, which is a big problem. Another reason you might care is that this invariant, the triple graded homology, is actually still really not very well understood. So I don't know if you guys are like me, but I don't feel like I understand a Lick invariant until I can do computations. And if computations are insanely difficult, then I don't understand what's going on. So there's something, there's a kind of a saying something I like to say, which is like most topologists use invariants to study topological objects, like knots and manifolds. But in this subject, it's kind of the reverse. We're using the topological objects to study the invariant. Because we don't understand the invariant, but we would like to. Okay. Yeah, it's very mysterious and kind of cool. And I can't avoid mentioning this. There's a very cool kind of family of conjectures relating this triple graded homology and then various of its cousins relating these things to Hilbert schemes. So this stuff may be, well, it is almost certainly connected in some almost direct way to these conjectures. So some names I should mention here are, so in no particular order, I guess, Gorsky-Negut-Rasmussen, Rasmussen, it's my attempt at alphabetical order. Okay. So, I don't know, I mean, anyway, I don't want to spend all my time talking about, it would take an entire day to just state all those conjectures, or even longer. But the point is they're really mysterious and they kind of point to some weird, not yet understood connection between triple graded homology and algebraic geometry. And when they first appeared, they were stated exclusively for torus links, or maybe algebraic links. So these guys play an important role in that connection. Okay, maybe I'll say more about this later. Okay, so the outline of what I want to talk about. So first off, I just want to tell you the technique and then how to compute torus links. So that's the most important part, and I have a tendency sometimes of going really slow in my talks, and so I don't actually get to what I want to talk about. So I'm going to talk about, I'm not going to define the invariant for you. I'm going to tell you how to compute it. So I hope that's okay. Kind of a backwards way of doing things. But this technique that me and Ben have, it's actually, like when it works, it's super easy and combinatorial. So you don't actually need to know the definition of Khovanov-Rozansky homology to use it. So this is the outline. So first off, the technique. Second, the application to torus links. And then I will explain why this technique works. So in other words, I'll have to define, actually give some definitions here. And then if I have time, I'll say something about this. So some predictions that are made on the Hilbert scheme side, and then how they kind of match up with what can compute. Okay. So the technique. And I want to be careful about how I use space. So here now. Let D be a braid diagram. Possibly with some boxes inside the diagram. And by box, I literally just mean some decorations inside a braid diagram, like so. Everything should be braid-like, so it should be sort of co-oriented. Okay. Suppose the closure of this braid diagram.
What does the box represent?
The boxes. Okay, so I'll explain this a bit more after a while. But the actual definition of Khovanov-Rozansky homology goes through a category called serial bimodules. So there's a So to actually define the homology, the way it works is to each braid, you associate some chain complex of bimodules, and then there's a functor that takes you from bimodules to vector spaces. And this guy represents a particular chain complex of bimodules that categorifies the Jones-Venzel projector, or a multiple of the Jones-Venzel projector.
No, I should think of it as a decoration on the.
For the moment, you should just think of it as a decoration in the braid diagram, but ultimately, the invariant of braids taking values in this category will extend to decorated braids. So there's a kind of mild extension of, like if you've ever seen the definition of the colored Jones polynomial, typically what you do is you start with a link diagram labeled by the integer k. You replace the diagram by k parallel copies of itself. Then you insert a little box somewhere. The box is some scheme theoretic element called the Jones-Venzel idempotent. And then you evaluate using the Kaufman bracket, just like you usually would. So the box is some formal linear combination of diagrams. And when you categorify, it's now a certain kind of chain complex. So you, so the invariant. So you should think of this as, okay, maybe I'll say more about this later, but you should think of this as representing a categorified Jones-Venzel idempotent. Okay, suppose the closure of this braid diagram can be reduced to a multiple of the empty diagram. Using a sequence of the following moves. Okay, now let me try to be careful about fitting these all in one place. So we first off have braid-like isotopies. So it really is important for Khovanov-Rozansky homology that you choose a braid diagram. You can sort of define an invariant for arbitrary link diagrams, but it's not preserved by Rademacher 2, by the unoriented Rademacher 2 or Rademacher 3. So when I perform isotopes, I have to be careful that they are all co-oriented. So, for example, braid-like Rademacher 3 looks something like this. With the various crossing data, braid-like Rademacher 2 is this, and then also the opposite orientations. The Rademacher 1 moves are all considered braid-like. In this talk, all of my links are going to be positive, so I will only ever need to use this positive stabilization and destabilization. So I actually don't want to add -1 to this list. It will actually destroy the statement of the theorem. There's something that I'm going to call box recursion. It's a sort of linear relationship between certain kinds of diagrams. So first up, if you see a lonely strand with no box on it, then you can add a box at the expense of this factor. This next relation, I want to emphasize that you have to be careful on utilizing it. It's unidirectional. So if you see this somewhere in your diagram, you are allowed to replace it with, and let's say this number is n. You're allowed to replace it with this linear combination. Actually, I want to consider this one as a special case of that one. When n is 0, that relation reduces to this one, at least one direction. Box recursion. There's another relation I want to call braid absorption. So this, in the end, is going to represent some kind of symmetrizing object. So it absorbs braids. Okay, just completely absorbs braids without penalty on the bottom or top. And then there's another relation that I want to call the short circuit relation. And maybe I'll fit that here, short circuit relation. Which is, you have a box, and two of the strands are connected up. Then, let's say this number is n, so you have a total of n plus 1 strands visible. Then this guy is t to the n, say. So it's pretty wacky. These are the relations, that's it.
You can just remove any braid for free?
Yes,
If you have that box.
if you have the box.
Mm-hmm.
So this guy just eats braids. Okay?
The box
So-
is something secret that you.
I will explain. The reason why I'm organizing my
Combination, it's not specific thing.
Yeah.
it is some very specific chain complex. And the theorem is it exists. You don't need to know what it is. But it has these properties. Or it has certain properties which reduce to this kind of combinatorics. Once you take homology. So the statement of the theorem is if you can reduce your diagram to the empty diagram using the sequence of these moves, then that polynomial is a Poincare polynomial. Up to a change of variables, that is the Poincare series of your triplet gradient homology.
Here you normalized using little letters instead of.
That's right, and I'm going to say how the little letters are related to the big letters. The statement of the theorem is then this guy, after you make this substitution, so remember Q was the Q degree in triple graded homology, T was homological degree, and then A was this third grading. Those are capital letters, and then I'm introducing these lowercase letters, which are just obvious change variables for them. So I'm lying a little bit here. I should have mentioned a second ago that actually HHH extends to these decorated braids. You know, braids with boxes in them. And then that extension satisfies this. Okay. Believe it or not, this is exactly everything that you need to compute the triple graded homology of torus lines. Positive torus. Well, positive torus links. Okay. So that's going to go here. Okay. Let's do some examples. So what about the unknot? So the unknot, well, it has a lonely strand. You can add a box to it. Okay, and then the short circuit relation gives you that. Okay, so that's the invariance of the unknot, which you can compare with the invariance of the unknot I wrote down way at the beginning. And modulo this change of variables is exactly the right thing. Okay, let me just tell you what the invariance of the sort of decorated unknot looks like. So if you just take a box with a bunch of strands and connect them all up and then get the unknot, you just use the short circuit relation over and over and over again. More interesting example, how about the trefoil? Okay, so that's a braid that represents the trefoil, of course. It has a lonely strand, so I may as well add a box, put a box somewhere. Actually, let me do it right here. Okay, and now if you focus on this little piece, you can use the box recursion, and when n is 1, you get the following relation. So this is t. I'll use the equal, I'm going to abuse the equal sign here. T inverse over 1 minus q times box. Okay. So two of the crossings sort of disappear and become either a box or the identity. Sorry. Anyway, I just said that wrong, but whatever. This guy absorbs crossings. Anyway, so when you close up all the strands, you get this kind of picture. This can be evaluated using whatever this relation that I wrote down a second ago. This one is a positive Rademacher away from being the knot with the box. Anyway, and you end up with T inverse over 1 minus Q times T plus A plus Q 1 plus A, and I guess when you rewrite everything, you end up with okay, so there's an overall T inverse here. Here's a copy of the unknot, and this is the reduced homology of the trefoil. The reason I've chosen these variables Q and T is that if you start with a knot, you would expect QT symmetry in the Q. So if you, up to some nonsense right at the beginning, involving some, overall monomial and also the unknot, the rest of it will be symmetric in Q and T. That's the reason why I chose those variables. Okay, Jake, is that okay? And establishing. All right, so it's pretty cool, right? I mean, if you were to actually use the definition of Khovanov-Rozansky homology, it would take you like a month to learn the definition, and then another like day and a half to actually compute this homology. I mean, like, I'm exaggerating, of course, but.
I mean, it is written down like in the end of Khovanov's paper.
I know. I mean, if you're a Khovanov, you can do it in like, you do it. My point is,
if you want to take more time, you can start with Mark 6 factorizations.
that's right. That's right. I mean, but the actual definition of this stuff can be kind of heavy if you don't like homological algebra. But the point is, you don't have to know kind of anything about that in order to use this technique. I should warn you though, remark. So how is little t related to big T? So little t that appears in these computations is actually t squared q to the minus 2. So any computation that you can actually perform in this way is automatically supported in even homological degrees. So any sort of triple graded homology which can be computed in this way is necessarily supported in even degrees. It just so happens that lots of things we care about are. So this parity is actually key to why this method even works to begin with. Homological, that's not right. Okay, so for example, this isn't going to work even for the figure 8, but it works for lots of knots. Oh, so what can I use? All right, so I'll leave that unchanged, but is it clear? So little t, so anything that can be computed in this way is always going to have integer powers of t, which means it's going to always have even integers. It'll have even integer powers of little t, so it'll have integer powers of little t, so it'll have even integer powers of big T. Okay, great. Now, for the main event. Okay. So, what I'm going to do is draw the class of torus knots, or torus links, and then I'm going to extend them into a class of diagrams that have boxes in them. And then I will recursively compute the invariance of all of them simultaneously. Okay. So how do I think about torus knots, or torus links? I guess this is strictly speaking. I'm taking a long time. All right. Maybe out of order. Whatever. So the NM torus link, I want to think of in this way. So I want to draw my pictures in this way because it'll save a lot of time later. So what I've just drawn is an embedded, like ribbon graph in R3. And I'm claiming that if you put these labels on it, and it actually represents a link in R3, given by, well, labeled strand, you just replace it by so many parallel copies of that strand. And then if two strands meet at a trigonal vertex, then you just do the obvious thing. Okay, and this is sort of a quick way. You can see this is like the one skeleton of an embedded function torus. R3, and this is a very convenient way of drawing toruses. So as an example, let me draw. Again, my pictures are not there. Okay, so as an example, C35. So, I mean, I'm going really slow, so maybe I shouldn't do this in detail. So if I were to draw the 3-5 torus now, what I would first do is I would try to connect up these strands in a planar fashion. There's a unique way to do that. Okay, and then I would take these 5 guys and these 5 guys and connect them, sort of go around the back of some cylinder. And I would take these 3 guys and these 3 guys and connect them this way. Okay, and that's all this picture is indicating. I'm writing in the neighborhood of a graph, embedded graph. Okay, so next I want to take those diagrams and extend it to a set of diagrams that have boxes in them. So suppose we're given integers k, m, and n, and we're also given v, which will be a sequence of zeros and ones of length k plus m, w, which is a sequence of zeros and ones of length k plus n, where v and w have the same number of ones. So given such data, I will define a diagram. So I'll denote it C, V, W. With it, and sort of schematically, this is going to be the same sort of picture. With orientations just like before. Except now we have some kind of interruption coming from so I'll draw it this way. These pictures look better in paper. Okay, so let's take n parallel strands here, m parallel strands here, and k parallel strands here. So I guess this number is m plus k, that number is m plus k plus n, this number is k plus n. Okay, and then, so I have k parallel strands here meeting n parallel strands. And the way they meet is going to be prescribed by W. And the way these strands will be, those M strands will be prescribed by phi. So the ones, the positions of the ones in V and W are sort of describing how strands feed into the white box. And the best way to do this is by an example.
Excuse me, in this picture, if k is 1, should you recover the other picture?
If k is 0, you'll recover the other picture.
So you connect on the other side. It's not the same if you arc with the box comes on the left or on the right.
Say it again.
Uh,
Yeah, I want to be careful about.
on the other vertex, I would put.
You would put it the other way.
Yeah.
Yeah, you can. Yes, you can also write it that way, but you want it to be braid-like. Is this your concern?
No, it's the point that if you start with small k, probably you want to have the other one, and then the merging.
I'll explain how this.
I don't see now.
Yeah. Certainly, when k is 0, you recover the older.
I'm concerned with
You're
the
concerned that
vertex.
the circle, the thing with the K is just going to split off a circle.
I mean, if you remove the box and then you separate one string among the n up there, then it will come on the other side.
Yeah.
The
So
same ones here.
I see. Yeah. Let me tell you what's going on here. This is actually funny. The way that these k strands merge with those m strands is prescribed by the sequence v. So depending on what v is. Yeah. Okay. So let me tell you how. Yeah. So let me tell you how v and w are actually entering the picture here with an example. So let's take k equals 3, m equals 4, n equals 2, and how about like 1, 0, 0, 1, 1, 1, 0, 1, 0, something like that, and comma 0, 1, 1, 0. Okay, so let me define this complex. So first off, I'm going to have n strands on the bottom. I'll have m plus k plus n strands on the right. Sorry, m strands on the right.
You have one more.
Yeah, one more in the last one is
Oh,
5.
thank you. Yeah, they should have the same number of ones. And then this will be 5. And this will be 7. Okay. So let me label brown the ones with the positions of the ones. So this is a 1. So here I'm counting down, top down, and here I'm counting left to the right. So maybe I'll label the sequences here. So this is 1, 0, 0, 1, 0, 0, and this will be 0, 1, 1, 0, 1. Now the ones are strands that are going to be fed into the projector. Sorry, into the box. And the zeros are strands that are going to avoid the box. And you want to do that in a positive fashion, so that all the crossings are positive. Okay, so this is what it looks like. Zeros avoid the box. Ones get fed into the box. Okay. And then everything else does what it should for a torus knot. You just connect up the strands in kind of planar fashion. that. These ones connect to those. And then these guys connect to these via the back of the cylinder. Okay, so that's a picture of the kinds of complexes I'm considering. Weird, right? Okay, so, however, these are the guys that appear in an intermediate step in this calculation. So these are pictures that you will basically find in Mellit's paper. I'll have a different description of them, but I should mention his name here. But anyway, they're also similar to picture, whatever. So this is what you get if you take Mellit's paper and try to make it look more like the paper I wrote a month earlier. Okay. Now the recursion. And in fact, I'm going like super slow, but I guess this is fine. I'll tell you the recursion, and then I can even prove the recursion. Because it's in fact super easy once you've defined these complexes, and then once you understand the recursion. You can imagine it's completely elementary, which is wonderful. I mean, for such an impossibly difficult computation, the fact that it reduces to something like elementary is, I don't know, pretty interesting. Okay, so what's the recursion? So this is a theorem which is, mostly Mellit's. I mean, really is Mellit. So let P VW denote the Poincare series of the complexes represented by those diagrams, which, strictly speaking, I haven't really defined yet, but this is the thing that can be computed using the technique of V and N. Then these guys satisfy the following recursion. So if both V and W begin with a 1, then you deal with it in this way. If V starts with a 1, but W starts with a 0, you deal with it in this way. So the 0 basically disappears, and then the 1 cycles around to the back. And this is totally symmetric with respect to the two arguments here. So conversely, if V starts with a 0 and W starts with a 1, I'm going to try to see here. So those are both part of recursion 2. And third recursion, if they both start with a 0, then you get right here up to overall factor of t, you get, so the zeros get replaced by 1s and cycle to the back. And there's also a term in which the 0s just cycle to the back. Okay, is that kind of clear what's going on? So things in the front tend to get cycled around to the back. The zeros tend to disappear, or they tend to get converted into 1s. And the more 1s you have, the better. Because as soon as you see a pair of 1s right at the beginning, you decrease the length of your sequence. it turns out you can actually, this uniquely characterizes the P's. And part zero of the theorem is,
Proving this, you have to prove a quasi-isomorphism in the complex constructed. with
Exactly.
some-
I mean, this
But
is,
you have to take care about the Rothschild homology when you close also.
so you have to take care that each of these is actually a braid-like isotopy together. You have to, so this is a direct application of the theorem of mean bends. So to prove the theorem of mean bends, you have to be careful about Hochschild homology and some spectral sequence argument and all that. But once you have that theorem, this is a direct application. And you don't need to mention the word Hochschild homology anywhere. So there are basically two halves. One is the sort of more technical part, which is proving the theorem of mean bends, which involves some, it's not hard, but it involves some short exact sequence or long exact sequence homology splitting kind of argument. And then the second is this application of it. I should also mention that if you just have the torus link, when this corresponds to the case when k is 0, so v and w are empty, you can insert a 1 at the end. This should be an n. And then up to a factor of 1 over 1 minus q. So if you start with that guy, you get yourself started by adding a 1 somewhere. Actually, strictly speaking, 0 isn't necessary because, again, 0 falls from 3. If v and w were all 0 sequences, then if you look at this recursion, you'll get this one as a special case. Cool. Are there questions about the statement of the thing? You guys all feel like you could prove it if you sat down and did it? You have the definition of the complexes. It's actually all right here. You could just take a picture of it. Like a one-page, like,
You
cheat
could
sheet.
assign this homework.
Yeah, it's a homework exercise. Here's the technique. There are the complexes. Here's an example of the complexes. And then there's a statement of the actual recursion. I didn't actually, plan for it to all be visible like this. Okay. So I'm not going to erase these because that's important. But let me just show you what this looks like. It's really not hard. So let's first off let me convince you of 0, the easiest one. So if you have a torus knot, or torus link, I'll forget the orientations most of the time. They always be in this way. Well, you could also sort of separate or unzip one of the strands. This guy feeds into here, but then it does this, and then it terminates here. Okay, so I'll draw that extra strand in brown, just to kind of distinguish it from all the rest. So this is just one lonely strand, and then the rest are bunched up. Okay, and we know we can add a box to that lonely strand. And then up to isotopy, this is exactly, you can just check. So what does this strand do? It does some redundant nonsense here, but then it connects up to the box. So I could actually, I'm kind of insulting your guys' intelligence by even writing this, but here it is anyway. So we have the box here. And then what's happening is, that strand connects up to the box, but it does so in some redundant way, which we may remove the redundancies and we get this. It's an exercise to check that that's actually braid-like. You can perform that using braid-like isotopies. And then this guy just goes back into the box. Which, if you like, let me draw it this way. And this is exactly what happens if you put a 1 on the far end of V and on the far bottom of W. So that's statement 0. Okay. Statement 1. So in this case, we have a 1 here and a 1 here, which means both of those strands are getting fed into the box. And then you have, V is something interesting, and W is something interesting. But this brown strand, you see, is just a trivial loop. This is a direct application of short circuit. Again, you have to convince yourself that that's actually, you can do that by a braid-like isotopy. You might actually be a little bit concerned because this Redomister screw move is, strictly speaking, not allowed. But anyway, exercise. You can do that by braid-like isotopes. I mean, this is, you can give this to your undergrad students. In fact, yeah. Okay. All right. How much? So we started a little bit late, right?
Yeah, probably started about 5 minutes late.
Okay. So maybe I'll wrap this up and leave the rest as exercises. And if you like, I can show you pictures that I've drawn. So I didn't actually say anything about the definition of this complex, but I want to not. I mean, I couldn't start it now and finish in 2 minutes. So we'll leave it at that, and then if you're curious, you can talk to me. Cool. Thanks.
So, supposing that you know the method works for some braid, and then everybody must have asked you this question before, but and then then you add a full twist to that braid. Does the method work?
I don't know the answer to that. Yeah, I mean, I don't know the answer to that. Another question which is harder is that if you take any braid and put enough full twists on it, does this method work? I mean, this, and not the answer to that I actually suspect might even be yes, because well, I don't know, maybe not, but
I mean, that's like saying that if you take any braid and you put enough full twists on it, then you expect the HOMFLY polynomial to sort of be positive.
yeah. Do you guys on the Hilbert scheme side, do you have any reason for expecting?
I wouldn't sort of a priori expect it. Like if I give you a single sheaf on the Hilbert scheme, then
There's no reason to expect that twisting it would.
no, I mean if I give you a single sheaf on the Hilbert scheme, I think that's true, like an honest to God sheaf.
Okay.
But like the thing is, I might have like I don't a priori see why I couldn't have like a direct sum of sheaves or something with a grading shift and have sort of two pieces that wound up with opposite, homological gradients. I mean,
Yeah, I don't know. I mean, even. Yeah, I mean that's a good question, but
That's maybe a question worth thinking about in the 3-strand braid case, where we sort of understand something about what to expect.
Maybe as an exercise, if you guys are really curious, let me just to convince you that this works for things that are not just torus knots or torus things. You can compute even within this framework. Utilizing these complexes for special values of v and w when k is a 1, compute, so show that these guys arise as special cases. Maybe with an extra. So certainly those links you can compute the invariant of, but you can also twist them by this sort of dual Garside thing, and then close up to get an actual knot. These guys actually occur as special cases of these diagrams.
Does the answer agree with what it's supposed to?
I don't know. I mean, I don't even know. It's the recursions that come out of this picture are completely different from the answers that are coming from the Hilbert-Scale side. So I don't have a proof of anything like that right now, but for 3-sign braids, yes, like you can do it explicitly. So I was going to say something about that, but I clearly don't have time.
Is there a hope to extend the moves so that you can consider more braids? I mean, in the Murakami-Yamada graphical calculus, you have reduction of squares.
Oh, okay. Right. It's a good question. I haven't thought about it. So these I should mention. So if you guys are familiar with the MOI kind of graphical calculus, what they do is they consider invariant. So they extend the SLN link polynomial or the HOMFLY polynomial to embedded trigonal graphs, which are oriented and in which the edges have labels that sort of add up in this fashion and near the vertices. And you can kind of categorize this graphical calculus as well.
You can
This
put,
is-
this is the same as 3 boxes, I guess.
These are actually dual. So these are maybe, you should think of them as being like wedge colored representations. These are like symmetric colored representations.
But
And the duality, but
duality is not, it's a good duality. At the level of HOMFLY, it's very easy to understand this duality.
yes, but when you categorify, the duality breaks down somewhat.
But I mean, this mode calculus, you can develop exactly the same.
Yeah, I agree. There should be some kind of relation, but it might not be as
It's
helpful.
completely formal.
Yeah, I mean, I think I understand. Like the symmetrizer and the anti, they satisfy exactly the same relations.
I mean, if you work just graphically with trigonal graphs, and maybe forms if you like, then you have no difference between symmetrizer and symmetrizer.
Right. When you categorify, though, it's a little bit weird.
Yeah, but there is a I have in mind maybe there is a form model for this.
Yeah, I mean, it would be great if so. I mean, one thing that you would want to understand is, like you said, the square relation.
Yes.
So you want to understand what happens when you do
Yes.
sort of things like this, and this doesn't have to be the same number. Is this what I want?
No.
Sorry, I want a square. Are you good?
It's a square, but in the more.
So this is like.
This is box here.
I don't know, put a box everywhere.
Yes.
And then you feed a bunch of strands here into there and here into there. Yes. so boxes everywhere. So this crazy arrangement of boxes. Yeah, it's certainly worth considering. I don't know. There's a, yeah. It should look a little bit different though from, we can talk about there's like an asymmetry actually that occurs.
How do you show that the result doesn't depend on the way that you use those moves? Do you do that? Is that proof combinatorial? Or?
No. It's the proof is there exists, an actual homology theory.
Right.
Inside and within that homology theory, there exists.
Okay, but have you tried to do that completely from a combinatorial point of view?
Yeah, it doesn't quite work out though because this. You have to actually be really careful and not abusing this kind of technique. So this rule is actually works only in one direction. You're not allowed to introduce minus signs anywhere. Because these are supposed to be Poincare series of something. And so you would want to do something like, I thought about actually when I was preparing this talk, I thought about phrasing it this way, but then I couldn't convince myself that it was well close. You could try to do something like, take the, so what do you call it? This is a monoid, or it's a semi-ring? Is that what people call this? Because you can add but not subtract, and you can multiply. Semi-ring, and you can also consider semi-modules over this ring. So if you look at a semi-module spanned by diagrams of this form, modulo all these relations, then you look at these sort of equivalence class of the empty diagram. Maybe the trouble is I'm not sure if I want to make this an equal sign. This chain complex is not actually the direct sum of these two things.
But they are quasi-isomorphic.
No, it's an extension. But once you take homology, the extension splits.
So the homology is the same.
That's right. So maybe I'm
It's a
concerned about.
quasi-isomorphism, right?
Yeah, maybe it's totally fine actually. But I want to be careful. Maybe this works completely. Yeah, maybe you can just define that sort of
All
semi-module.
that you need, or maybe I'm wrong, but maybe all that you have to show is that the moves commute with one another. Or is that, maybe that's wrong. Yeah, I'm not sure, but
The best way to show consistency of a bunch of relations is to show that it's represented somewhere. Like
In this homology theory that already don't exist.
yeah, and but yeah, so maybe I'm being too careful. Maybe this is actually obviously consistent if you just so maybe you don't need to mention homology anywhere. You just define some sort of semi-skein theory.
Implicitly, you have a graphical model. And then this graphical model you can represent with this point H.
Yeah, I
And
probably
probably the invariance you can show at the graphical. You have certain relation, graphical relation.
yeah.
Probably there are enough to show invariance at the graphical level.
That's definitely worth thinking about. I haven't spent too much time thinking about it, like proving consistency combinatorially.
okay, but you know that it is consistent because you have the other. Okay, so when you say you're not sure whether this works in general, the question is, do you always get down to the empty diagram? Is that the problem?
It's certainly not true that you always get down to the empty diagram, because there are examples of knots that don't have this parity condition. So the figure eight has. Yeah, and so this is maybe an interesting question that you can now ask. what is the actual class of links that can be computed in this way? And somehow, like when I was a grad student and I heard all these conjectures about torus knots, the first question is like, what's so special about torus knots? Well, of course they're special, but like, what's like, and so in some sense, the thing that's special about torus knots is that they can be computed in this way, or like that's one thing that's special about them. But there should be a huge class of knots for which this works as well. Like, so if you take the full twist on k strands, you think of it in the n strand braid group, just by adding strands to the right. You look at the subgroup of the braid group spanned by these guys, and maybe I should say semi-group. I want positive powers of them, not negative powers. But if you take positive powers of various full twists, and then top them off with like something like this, or maybe not the full thing, but a product of smaller nodes. You top it off with something like that and pulls it up to get a link or not or whatever. Conjecturally, there should be a nice answer or a computable answer for those. So, and it should be even, it should have this even property. So, research level, homework, exercise, problem, whatever. Compute the invariant of those using this technique. So that's a huge class of links, which is not torus links, but is amenable to this kind of construction.
Is there anything you can compute? Oh, sorry.
Yeah.
Is there anything you can compute it? Which is not coming from this method?
Oh, me, no. Like the only thing that, so you can't, the figure 8, I guess, but you, Jake, what did you say?
Two bridge knots.
Two bridge knots? Oh, two bridge knots.
But is there?
Is this you?
Oh, that was me.
That was you.
Or maybe I computed it for like SLN homology, but it's.
Yeah, two bridge knots. And then, right.
And you know that it's not this method.
Yeah, I mean, two bridge knots are sort of like exactly the opposite of what happens in these things, right? I mean, here, if I look at a single power, if I look at things in a single power of A in the HOMFLY polynomial, then all the homological gradings have the same parity. Whereas in a two bridge knot, it's just like what happens in non-floor homology, right? If I look at a single power of A, then the homological gradings alternate as you increase the power of Q, just like they would for an alternating knot in non-floor homology. So that, they're completely different looking from.
You can kind of combine this stuff though with various like spectral sequence arguments. So one reason why I'm a little bit, well, okay. So what I've stated here is a purely combinatorial version of the story, but there's a each of these identities corresponds to basically some distinguished triangle in some triangular category. So like what I'm really saying is that there's some chain complexes or the bimodules, some trio of chain complexes that fits into some distinguished triangle. And then when you take homology, you get a long exact sequence, and then that long exact sequence splits. So you get this relation. But even if you're in a situation where this method literally, like strictly speaking, doesn't work, you can still try to apply this technique at a more sophisticated level, like the actual homological algebra level. And you get all kinds of spectral sequences popping out. So for example, the figure 8 you can compute, in other knots, presumably work the same way. You can compute it by attempting to use this technique in two different ways. Like two different sequences of moves give you two different sorts of expressions. And there might be a differential here, but you don't know because you can't actually see the differentials from this picture. But you can prove that it is there or isn't there by So anyway, the usual spectral sequence kind of nonsense. Like you never know if there's a differential in this page of spectral sequence. Like you can almost never just compute it by hand. The best way to do it is to compute the same thing in two different ways. And observe, oh, there's a pair of guys that could annihilate one another. Do they or do they not? Well, you look at some other spectral sequence and they're not there. So you would conclude that they... Anyway, I'm sorry, I'm rambling, but you know, there are plenty of ad hoc ways of using this technique that have not been exhausted.
Another question. Is there a chance to make sense to those boxes for Hilbert?
Ah, yeah, that's a great question.
This spectral sequence.
That's a good question. Yeah, I've been thinking about this. Should be. Jake?
I don't know,
Okay.
you know, the thing that we were talking about, you know, seemed to make sense, and you know, for example, it does eat braids.
Yeah.
You know,
Yeah, so I'm, yeah, this is something that I started thinking about recently, so I don't. Yeah, I mean, I have two great people to talk to about it, so ask me again. So, yeah. Yeah, it should be. I mean, do you know? I mean, if you take if you take your complex for the full twist braid and take powers of it, does it have some kind of limit? Do you know? It's been.
I would suspect it doesn't. Like for,
Well, if you normalize away the factors of 2 that appear.
I don't know, I mean, there is an answer for this for, like, if you introduce monodomain, just border for homology, twisting, then it gets just arbitrarily big.
Mm.
But I mean, your box is not
Okay.
the honest Jones-Venzel, it's the sort of unnormalized thing.
Yeah.
Right? So the unnormalized thing, I think, might be
Easier to look at. Yeah. So probably, but I'm still learning some of that stuff. So. Yeah, and in fact, it should even look nicer, maybe, because there's lots of, well, I don't know, like. Let's talk about that later. Are there cookies or pie or something?
Is there cake, Pelham?
Oh, okay.
Sorry. We have to thank Pelham.
Okay.
But we should also thank Vatican. That's right.
Or just after Friday.
Oh, I should have mentioned, I think somebody asked about color homology in that talk in April. You can also get, so this guy is like a normalized version of the Jones-Venzel. And so you can also obtain colored invariants of torus knots by the same kinds of diagrams. All you do is you just, let's write it this way. If you want the L colored homology, you replace n by n times L and m by m times L. And then you look at the sequence V and W that has you take the last L elements and you replace them with 1s. And then that's if M and N are co-prime, this is the color homology of that. So it's no harder than the other. Okay. Thanks.
Let's go.